Welcome back, beautiful primates. Today we're going to take the next step in our journey into inferential statistics with a look at ANOVA, which stands for Analysis of Variance, specifically the two-factor ANOVA. Alright, so I don't know about you, but sometimes for me it's hard to know where to start a project, so I like to try to attack a few simple steps first and build some momentum. So here I've taken the liberty of inputting my times into a spreadsheet. I've already converted them over from minutes and seconds to total seconds like in the last video. Alright, so the first thing I'm going to do is I'm going to separate this group, which are my knockout flies, from this group, which are my controls. I'm going to separate them vertically and put these underneath. So first I will copy all of this, and then I will scroll down a ways, and I set this at scroll down to row 28 and paste it in. Now the reason for that empty space will become apparent later. So and then we'll take these and we'll cut those out, and then we'll come down here and paste them. All right, we'll make a little more space for all of our words to fit nicely. So the next thing is let's go ahead and pad the distance between these two columns a bit. We'll add 2 columns, and we'll pad this one to the left 1 column also. Okay, so now we should have one set up here with our HSPs and one set down here with our controls. Now right off the bat we know a few of the things we will need to calculate. Since ANOVA is kind of similar to a t-test, we might expect that we might need means, and ends, and degrees of freedom, and so on. So we can start with a few of those steps, and then we'll dive into the math. So let's start here in column B, and the first thing we'll calculate is the mean. Pretty straightforward to do. We'll just use the formula equals average of those cells. That's the cells we want. We'll hit enter. Okay, we will copy. Actually, let's hold off on that for a bit. We'll save a little time. Step 2, we'll calculate the standard deviation. Not that we need the standard deviation elsewhere in this calculation, but it's nice to see. It gives us some idea of what the variance looks like, what that distribution looks like. And we might also want to include that in our results. So we'll take a bit of a shortcut this time, and we'll use the standard deviation function that's built into the spreadsheet, but we'll use the .s version of it for specifically for a sample. If you calculate standard deviation for a population, remember it's going to use n for the denominator, and for a sample of a population you use degrees of freedom, which is n-1. That's the difference between those. So we use standard deviation.s, and we will highlight this range, close the parentheses, and there we go. Well, we don't need this many digits. Thinking about significant figures. Okay, so step 3, we'll calculate an n. And so remember, this is the number of samples. And we'll do that with the count function. And it doesn't have the right ones. We'll take these values, enter that. All right, so step 4, we might as well, since we're right here and it's easy to do, we'll calculate our degrees of freedom, which is going to equal this minus 1. Now we want to repeat all of these things for this other column, so we'll just we'll copy these formulas, and we'll paste them right over here. And note that it's calculating the correct values for this column. And now, here's a little fun. We can take this, we can copy it. Now we'll come down here and we'll copy it in the same position underneath these other columns. All right, so far so good. Now, let's dive into what the underlying math is. So imagine for a moment that we are sort of like doing simultaneous multiple t-tests. So we could theoretically do an individual t-test for the different ways that we're trying to pry this apart. So for example, we could combine our A's, males and females, and compare those to our B's, males and females, all together. We could do a t-test on that. And we could combine them the other way. So we could combine the males of both control and experimental and the females of both control and experimental and do a t-test on those. However, there's a small problem with that. Every time we do a t-test, there's a margin for error. We run the risk that we could get a false positive every time we do a t-test. And so if we do a t-test with one set of data and then flip the groups and do another t-test, we have to multiply those errors. Those errors accumulate. The solution to that is ANOVA, and we can do this sort of all in one fell swoop with only one margin of error. What we can do is we can, as I said, we can combine the A's together and compare them to the B's, or we can combine the males and the females and compare them. But that's not all. There's one more thing we can do with an ANOVA that I don't think we could do with a t-test, and that is to test for interaction. And what that basically means is, does one of these factors feed off of the other? Does changing one factor increase the effect of another factor? So there's a fun and easily memorable example of this interaction phenomenon from my statistics textbook that goes a little something like this. So this enterprising group of social scientists divided their subjects into two categories of self-esteem, high and low. And then both of these groups were further divided in half in an experimental condition on whether or not they were watched during a test. And I don't mean just watched, but like they brought in TV cameras to watch. So this would, let's say this is the no camera, and this is the camera. And the test, basically, the data they collected, the independent variable, was the number of mistakes that these students made on this exam. So this is what we mean by two-factor. One factor is self-esteem, and one factor is watched, and then so we can see there's four different groups here. And that's why I've divided the spreadsheet up this way. So what they found when students were not watched is that the students of high and low self-esteem had about the same number of mistakes. Let's just give that some random value like 4. And then when they were watched, the high self-esteem group goes up to 6, and the low self-esteem one rockets up to 10. So this is what we mean by an interaction. So we can see that there is a main effect. We can see that there is a main effect of being watched, right? So when they were watched, both groups of students made more mistakes. Now, we could say that being watched is responsible for some amount of the variation here. And in this case, it's probably fair to say that it's also responsible for some amount of the variation. But what accounts for this difference? This is the interaction. And we write this up as generically A cross B, or in this case, it would be self-esteem cross watched. And over here, one more thing, there is no main effect of self-esteem because these both did the same before being watched. So we found a main effect of being watched, no main effect of self-esteem, but we did find an interaction between the two. So those can vary independently. So back to our squares idea. Here we have our experimental condition. So we have our knockout flies, and we have our control, and we have sex as the second factor. Now this looks like exactly how we set it up in our spreadsheet, right? Like last time, we'll work our way backwards through the math. step by step. The number that we are after, the very final number that we are after in an ANOVA is the F statistic. And there's going to be 3. So I suggest writing this down in your notes because you'll want to be able to refer back to these equations as you build your spreadsheet. So the first one of these will be the effect of the HSP knockout. The second one will be sex. And this one will be both. So this will be HSP cross sex. This is our interaction. So our F statistic for the HSP is going to be equal to the mean squares for HSP divided by the mean squares within. So the reason I'm color coding these is to make it really clear we need to keep track of multiple values that have the same name. It's really easy to get lost. Okay, so I've abbreviated the rest, and you'll note that the denominator is the same in all 3 cases. It's only the numerator that changes. Now, how do we calculate these numbers, these mean squares? So you can see that we need 4 mean square calculations. We'll need a mean squares for HSP, 1 for sex, 1 for interaction, and 1 for within for that denominator. You got that in your notes? Good. Okay, so on the numerator, we have the sum of squared deviations. Now, point of confusion. This is a thing that is going to come up in a minute. Sum of squared deviations is a different thing from sum of squared values. Now we're going to be calculating both, and unfortunately these are both abbreviated in my textbook as SS. So typically when they say SS, and we report this later, what that means is this: sum of squared deviations. Sum of squared values is a different thing, and we'll keep that clear as we go along. In our denominator, we have degrees of freedom for HSP. So, heads up, each one of these has its own degrees of freedom and its own sum of squared deviations. And this is another way that we can write sum of squared deviations, just so we keep track of it. It's the x value minus the mean squared. Again, just one reminder that anytime we see this SS abbreviation from here on out, that is the same thing as this, the sum of squared deviations. So you will now note there are 4 separate sum of squared deviations values we need to calculate next, and there are also going to be 4 degrees of freedom calculations to make. So remember that thing I said to watch out for about that sum of squares thing? So this is actually the sum of squared values. And all we're doing here is we're taking all of our x values, we're squaring them, and then we add all of them up for each of our 4 groups. And we total them all. So this is a grand total for all 4 groups. We take all of the squared x values and add them up, and then we subtract g squared over capital N. So g squared, this is the grand total of x. So just all of the scores, we add all the scores up and then square that. So that's different from this. Here we take all of the scores, square them, and then add the results. And here's we are totaling up all of the x values and then squaring that. And then n is just equal to the total number of samples. All right? See, it helps to put it in words. So then we have our sum of squared deviations within. So that's equal to the sum of squared deviations for each treatment. So we have 4 of those, HSP female plus and HSP male, and so on. We add all those up, that's our sum of squared deviations within. So now that we have those 2 numbers, we can calculate the between, and that's just as easy as taking the total and subtracting the within. Now, supposing you want a sanity check to make sure that this math works out okay, we can also arrive at the SS between with this formula here. The T is the total of scores for one of the treatments, of which we have 4. So that's the total squared divided by the n, the number of samples in that group. So, and then add all 4 of those up, and then subtract. And this is the same as this up here, the g squared over capital N. So that's the grand totals. Okay, so I know this is exhausting already, but these are the last things we have to calculate. The degrees of freedom within is just the sum total of the DF from all the groups. The degrees of freedom between is the number of groups, which in our case is 4, minus 1. And there's another way that this is referred to. The number of groups is also called k, so k minus 1. Now, the degrees of freedom for our treatment conditions go by rows and then by columns, right? So we did the HSP versus control in rows, and we did the females versus male in columns. So with the rows, the degrees of freedom this way is going to be the number of rows minus 1, which I've noted is 1. And this is the same idea here. The number of columns minus 1, which is also 1. And then the degrees of freedom for the interaction is the same as the degrees of freedom between minus the degrees of freedom for the HSP minus the degrees of freedom for sex. So it's just what's left over. Now that's everything we need to finish up our spreadsheet. If this is all a little much at the moment, don't worry, just follow along step by step and we will get to the right answers. Alright, so since we will need totals of scores to get our t-squared values, we'll start with that. So this is going to be equals sum, but we don't want these. We want these values. Okay, and then the next thing we'll calculate is the sum of squared scores. So that sum of x squared that we talked about, the one we don't want to confuse with sum of squared deviations. So as it turns out, there's a built-in function for computing this, and it is sum SQ, sum of squares, which see why this is confusing? There's no consistency. We'll highlight these values again, close our parentheses, hit enter. All right, so now we have that number. Now the next one we're going to do is the sum of squared deviations, which is the difference between the x value and the mean squared. And there's also a built-in function for this, which is really nice. So we're saving, we did this in several steps in the last video. We're going to do that in one step here. So that's going to be devSQ, sum of squares of deviations. And we'll put in that range. Now let's take these and copy and paste over here for this other column. And we'll take this whole mess, these steps 5, 6, and 7, and we'll copy those and paste them down here. Now step 8, I'm going to add some row totals. So we're going to sum up everything from left to right. So we don't need to do that for the mean or for the standard deviation. We don't have a reason to do that. But we do need totals for our n's, for our degrees of freedom, for our score totals, and for our sums of squares and squared deviations. So we'll do that with an equals sum, this, and comma, and this. All right. And we can just copy that right on down for the rest of these values. We don't need this 0 here. We'll delete that. Now these 5 things are going to apply down below, so we'll copy and we'll paste those down here in the appropriate square. And now we have row totals. Okay, so we've totaled up our rows. Now we need to total up our columns, and we'll do that down at the very bottom. So step 9, we'll calculate an n. So this is going to equal the n from the upper group and the one below it. So this n plus this n. So we had 15 up here. We had 14 here because one was dead. And we have 29. Great, that's exactly right. So step 10, we'll get the degrees of freedom. And that is equal to this minus 1. So equals this minus 1. Next, let's grab the score totals for the column. So this is going to be equal to, now it's not really easy to autofill this, so this is going to be equal to this score total plus this score total. All right. And then step 12, we'll have our sum of squared scores, which will be equal to sum of squared scores plus sum of squared scores. Okay. And step 13 is our sum of squared deviations, which is going to be equal to, in this case, C26 plus C53. Now we'll copy and paste these formulas over for the other column. All right, now we have column totals. Okay, we are almost there. So step 14, we need some grand totals. We can go about this two ways. We could total up vertically, add the rows together, or we could total up horizontally, add the columns together. So in this case, we'll make it easier on ourselves because it's right there. So we'll just do this. We'll do an equals sum of this and this. And so that'll give us a total n for our whole experiment. And we could, since we're taking totals of all of these, we'll just drag our formula down. And now we have totals. We can get rid of that 0. All right, now the very last step is to put together our ANOVA table and do our last few calculations, which we can do right in our ANOVA table. So we'll scroll down here, give ourselves a little room. Okay, so quick interjection here. I made a mistake and I discovered it when I was trying to track down my math. So when I told you on step 10 here, so back up a step or two, on step 10 here when I said to take the n and subtract 1, we don't want to do that. We want to add the degrees of freedom from the top and the bottom, and that's not the same number. So bear with me a moment here, and that is going to be our degrees of freedom from this sample plus the degrees of freedom from this sample. And now that should be correct. And now we'll take this, we'll copy this formula here, copy this here, and now we actually have the right answer. So sorry for the confusion. So now I've removed myself from the screen here to make some room. And over here, take a moment, pause your video, and just replicate this whole table just like this. So this is an ANOVA table, and it's a way that ANOVA results have traditionally been reported. So if you set this up in your spreadsheet, it's a pretty simple matter of copying and pasting it right into your report. So we have a column for source, one for degrees of freedom, one for sum of squares, one for mean squares, one for F ratio, and one for the p-value. So in the source column, we divide up between, within, and total. And the between is divided 3 ways, between our 2 factors and interaction. Now we know what some of these are, right? So our total degrees of freedom is our big N, so that's this value here, which is 59. We have 59 total samples, minus 1. All right, so this is going to be equal to our total N, which should actually be capital N, minus 1. And we'll go ahead and put a note right here to reflect that. That is our total N. Now the degrees of freedom between, this is the number of groups, minus 1. So we have 4 groups, minus 1, that's 3. We'll just punch that right in. The degrees of freedom for HSP, we have 2 rows, minus 1 is our degrees of freedom. So we have 1 degree of freedom for that. We also have 1 degree of freedom for sex and 1 degree of freedom for interaction because there are 2 factors. That leaves the within. So the within is simply the total minus the between. So this value minus this value. So we can put that in. The total minus the between. And you can refer back and see where the math is in your notes. So the next thing we'll calculate is the sum of squares total. And remember, that's this formula here. So our sum of x squared is this. That's our sum of squared scores. And then minus the score total squared. So that's this value. We square that and divide that by the total n. And that's going to look like this. So that will be equals. We'll open some parentheses. We'll take our sum of squared scores and we'll subtract and we'll open some more parentheses. So our score total is this, and we will square that and then divide that by the total n. Okay. And then next, our sum of squared deviations within is simply the total of all of our squared deviations. And then lastly, our sum of squares between is simply the total minus the within. Total minus within. And again, refer back to the math on that to make sure I'm doing this right. Okay, so this is our formula for the sum of squares for the HSP. Now this is the sum of, we total up the score for each group and square it and then divide it by the n. So we're going to have two values. So basically it's 1 t squared over n plus t squared over n, and then we subtract this g squared over big N, again, just like we did when we calculated the sum of squares total. We'll start with the rows. This is equal to, and we're going to have some nested parentheses here. This is equal to our score total from row 1 squared, the row total 1 squared divided by the n for that row, plus, and then we do the same thing for the other row. So our score total is here, and we'll square that, and then we'll divide that by the n for this row. And then we subtract that g squared over n value. That is going to be the grand total score squared divided by the big N. We can close all that off, and there we go. Now it's the same thing for sects, except we do it for columns. So we'll take our column score total here, go equals, open parentheses. We'll take this column score total, we'll square it and divide it by the n for this column, and we will add the same for this. So the score total here, oops, let's open a we'll go with the score total here and square it and divide by the n for this column. And then we subtract that same g squared over n value. So our score total squared divided by our capital N. Close that up. Okay, there we go. Now, the sum of squares for the interaction is simply the sum of squares between minus the HSP minus this x. So it's whatever is left over. And that's the unexplained leftover variation that we're looking for. So we'll take equals. Now we have the between minus the HSP minus x. Okay, and that's that. And now we recall that the mean squares is simply the sum of squares divided by the degrees of freedom, and we can do this whole column in one shot. So we'll take our sum of squares, divide by degrees of freedom, Control Enter to autofill, and we are good. Now we don't need the total here. We'll go ahead and delete that. Okay, and recall from your notes that the F ratio is equal to the mean squares of our category divided by the mean squares within. And we don't calculate one of these for between. We only calculate it for these three. For the HSP, this is going to equal to the mean squares of HSP divided by the mean squares within. Now, we want mean squares within for all three of these. So we're going to go ahead and lock this with the $sign. We'll lock the row and we'll lock the column. So we want it to use that same cell for all three of these calculations. And it's got our autofills right. We just don't need these two, so we can go ahead and we'll just delete those. So at long last, we have our F ratios. We have our F ratio for our HSP, our F ratio for sex, and our interaction. But what's our critical value? Well, we need to find that out. And I'm going to go ahead and grab critical values for 0.05 and 0.01. Now to find our critical value, we could look that up in a statistical table, or we can use the built-in function, which, if you remember from the last video, is related. It's F inverse. Now the probability that this function is asking for is our alpha value, which is 0.05, degrees of freedom 1, and degrees of freedom 2. What this means, degrees of freedom 1 is the lowest number, so that's our 1 here. And then our degrees of freedom within is the second number that it's asking for. So it's the degrees of freedom in the group, the degrees of freedom within. And this is how F scores are usually reported too. Like you'll see the F and then the parentheses and then a number and a comma and a number. That's the two different degrees of freedom. 4.01. Or 4.02. Now we'll take this one and we'll copy it here, but we'll change the formula. We'll change this to 0.01. So now we have our critical values. Did we exceed them? Well, okay, so our effect, our main effect of gene knockout, our HSP versus our control, is 4.17 compared to a critical value of 4.02. So we did surpass our critical value by a little bit, not a lot, but we did not reach our critical value for alpha equals 0.01. In the case of sex, so males compared to females, 5.91 is our F ratio. So this is a bigger effect actually. That surpasses our 4.02 pretty strongly, but it doesn't reach that 0.01 critical threshold if we set our alpha at that. And then lastly, our interaction, there's almost no interaction. This is very, very low. Now the very last number we're going to calculate is our p-value. And this is the function f dot dist dot rt. This is what we want. This is the right-tailed f probability distribution. Now the x value that we're going to give it is the f ratio, comma, the degrees of freedom 1, again, is 1, and then comma, the degrees of freedom within is this 55. Now we want to lock this degrees of freedom within. We want to lock this one with the dollar signs because that's going to be the same, and close parens. So what these mean is the likelihood that we would get a higher F ratio than this if we ran this test again, if it's random noise, is 0.046, so less than 5% probability. But that is still almost 5% probability that we could be seeing this effect by random chance, and there's not actually an effect. The probability for this F score for interaction, or sorry, for main effect of sex, the probability of getting a higher score then that F ratio is much lower. And so you can see these relationships now, 0.018. So that's about a 2% possibility that you might randomly get a higher score than this if there is no effect. Here, this is 53% likelihood that we would get a higher score than this. So this is not remotely significant. And the significance of these depends entirely on what we have chosen for our alpha. All right, so that's two-factor ANOVA. Not too scary, step by step, just like it's like eating an elephant, right? You just take one bite at a time. One bite at a time, you'll get through it. You'll end up with your statistics at the end. And moreover, you will be a spreadsheet ninja, and you will be able to convert other kinds of math in the spreadsheets into your toolbox. So use your toolbox, have fun. We'll see you next time.